Hi everyone, I'm Francesco, and today we'll present the paper Listenable Maps for Audio Classifiers, co-authored with Mirko Ravanelli and Sam Subakan. As you might know, deep learning models are generally black boxes, and this can be a problem for decision-critical applications such as healthcare. One way to go about this is to use explainable models, which might lose a bit in terms of performance. Or another way to go about this is to use post-hoc explanation techniques to generate post-hoc interpretations of black box models. One example of such techniques are saliency maps that are commonly used in computer visions that generate the saliency map that highlights the specific portions of the input image that are deemed important for the classifier decision. So it's important in this case that the saliency maps faithfully follow the original model, that is, they are interpreting. Additionally, it's also critical that the generated maps are understandable in order to actually gain some knowledge about how the model is working. In this paper, we propose an understandable and faithful post-hoc explanation method for audio classifiers. We worked with sound event detection, and I will just show you an example of what we propose is able to do. So here is an input audio. So this sample is a mixture of cat meowing and uploading, and the classifier predicted cat meowing. So as we expect, in the explanation, the cat meowing is highlighted. Our method is agnostic to the classifier input domain and can always generate listenable explanations. Additionally, we propose a fine-tuning strategy that improves the understandability-faithfulness trade-off. So to summarize, what we would like to obtain are faithfulness, listenable, and understandable post-hoc explanations for audio classifiers. The way we do this is by proposing LMAC, which stands for Listenable Maps for Audio Classifiers, that works by taking a pre-trained classification network that uses an input representation of the input, generates some embeddings that are later fed to the classification head that predicts the probability for each class. And then we train a decoder on top of the classifier representations, and the output of the decoder in this case is the saliency map. In order to generate the explanation, we then multiply the input representation with the predicted mask, obtaining the explanation. To ensure that the explanations are faithfully following the model, what we do is we feed the explanation through the classifier, and we designed a specific masking-based loss that ensures that the model is faithfully following the classifier. The way the optimization objective works is by taking the input audio and the generated saliency map and actually generating the explanation, which is taking the product between the mask and the input audio. And then we maximize the classifier agreement between the input audio and the explanation. That is to say that if the input audio was making the classifier predict cat, as in the example above, also the explanation should make the classifier predict the same class. Additionally, we wanted that all the portions of the audio that are related to the predicted class are inside the explanation. And in order to do that, we use a second term which minimizes the classifier agreement between the input audio and what is not in the explanation, that is the masked out portion of the audio. Finally, we also add a regularization term, which is an L1 norm on the predicted masks to avoid trivial solutions such as an all-ones mask. In order to produce listenable explanations, we cannot work, not always at least, work in the input domain of the classifier, because such as in this example, the input domain of the classifier might not be invertible without approximations. In order to solve this problem, we introduce a deterministic transform between the STFT domain and the classifier input domain. And by doing this, we can generate the listenable interpretation by simply using the inverse STFT transform. To measure faithfulness and understandability of the generated saliency maps, we use two sets of metrics. One set is related to faithfulness that measures the importance of the explanations for the classifier decision. And the other set is related to the structural metrics that aim to measure the understandability of the generated explanations. Finally, to improve the audio quality of the generated explanations, we add another regularization term, which is a fine-tuning term, that improves the understandability and is only used in a second stage selectively. So let's check out an audio sample of the effect that showcases the effect of the fine-tuning stage. So here is the input audio. So the input audio in this case is pig with some background noise, and the generated interpretation without fine-tuning sounds like this. So as you can hear, the pig sound is present, but the audio quality is not, it can be improved. And also in the second portion of the audio, there is the sound of the pig sound is has a super low volume. By using fine-tuning, we can improve this, and the interpretation will sound like this. So you can hear, and also as you see from the spectrograms, that the pig sound is better preserved. To evaluate the saliency maps quantitatively, we use two sound event detection datasets, namely ESC50 and Urban Sound 8K. And we experimented both in the in-domain and out-of-domain settings. In the in-domain setting, what we did is we evaluated the interpretations on the same data distribution that the classifier and interpreter were trained on. For the out-of-distribution experiments instead, we evaluated on a different data distribution that is generated by feeding the classifier and the interpreter mixtures generated with different contaminating sources. What we observe numerically from the in-domain setting is that LMAC is state-of-the-art in terms of faithfulness metrics, that fine-tuning is not harming faithfulness significantly, and that generating listenable explanation does not decrease the alignment with the classifier. That is to say that you can both work in the listenable domain, so using STFT and the deterministic transform, or directly on MEL, and you will achieve similar numbers in terms of faithfulness metrics. Finally, we're also better or comparable with the baselines in terms of structural metrics. We observe a similar trend in the out-of-domain setting where we use ESC50 mixtures samples to generate the OD mixture. And we also observe the same outcome both for in-domain and out-of-domain settings for Urban Sound 8K. And you can check out the appendix of the paper for the numbers. Finally, to evaluate the user preference on the listenable explanations, we conducted a user study in which we asked users to rate how well the explanation is corresponding to the part of the audio associated with the predicted class. And while doing it, we also asked users to evaluate the audio quality. What we observed from the results is that LMAC is outperforming L2I, which is a recently proposed postdoc interpretability approach for audio classifiers. We can also play one example from the user study. So this is the sample. In this case, the mixture is generated with dog barking and baby crying, and the classifier predicted dog barking. Here is the LMAC interpretation. So as you can hear, the dog barking sound is highlighted. Let's listen to the L2I generated interpretation. As you can hear, also in this case, the dog barking is highlighted, but it's also keeping a portion of the audio related to baby crying. Another example is this one, in which we use some LJ speech segments to contaminate the input audio to generate an out-of-distribution sample.
Palmer, too, showed an indecent haste in preparing the body for interment.
So in this case, the classifier predicted fireworks, and the contaminating source is a speech sample, and the LMAC generated interpretation sounds like this. So to conclude, we propose a post-hoc explanation method, which is state-of-the-art for audio classifiers. Our method is agnostic to the classifier input representation and generates understandable, listenable, and faithful explanations, both in the in-domain and out-of-domain settings. We also release our code inside SpeechBrain together with the pre-trained models. We conducted also a follow-up work in which we applied the LMAC framework on zero-shot classifiers, namely CLAP. Thanks for your attention. I'm happy to answer any question.